recently over the colored dots, the bright dots on the arts part sample. I've been trying to be able to come up with at least a good enough argument on why I think they possess symmetries that are useful. So that's been most of my analysis recently. So first off, what the heck's a quasicrystal? A regular crystal is periodic, right? Quasicrystal, aperiodic. You can see shapes in there. You can see these lines in there. So there is some level of periodicity. There is some level of symmetries in there. But the ratio distances between these red dots has the golden ratio in it. That's like one of the hallmark features of quasicrystals is golden ratios all throughout the thing. Fibonacci sequences, golden ratios. Here is another picture of what a quasicrystal looks like. Once again, ooh ah, pretty symmetries. And you can see how different dots are different sizes. Part of the reason for that is because a quasicrystal is kind of like taking a shadow of a three-dimensional object projected down onto a 2D surface, right? So this would be kind of like the farther away parts of that 3D crystal structure being shadowed or projected down onto the flat surface. That's the whole gist of quasicrystals, is that they are higher dimensional objects being projected down to lower dimensional space. All right, so this is part of the issue that I've been having in doing our quasicrystal analysis on this. When I went and visited Mark in November to do more testing on the sample, we had it on the schedule to do more scanning electron microscopy, specifically on these spots and other spots on the sample, to be able to get way higher quality photos of all of these organized dots here. So unfortunately, we canceled that because the opportunity came up to do some isotopic analysis. And so that sample is currently undergoing some really long tests to be able to find out all the isotopes that are in there. And we already have some preliminary results on that, but we're going to hold off presenting those results until we're done with the much longer test that has a lot more info in it. Anyway, so these are cell phone shots that Mark took with his cell phone of the computer screen of the scanning electron microscopy stuff while it was going, which is why it's so stinking blurry and why you got some of these like lines on there. And yeah, so I've been doing the best with what I got. But I think here you can see we got like some straight line guys in there. Over here we got like these two straight lines coming up and down. You got like this triangle over here. It seems like there's some lines on these things. So what I've done is I've taken this original one here and I have extracted just those dots, and I have associated the sizes here. See how that's big and white, little white, big and blue, little blue, right? I've kind of tried to extract the sizes and I've made them all round just to make this easier to analyze. First thing I did was I checked the sizes of those dots to see if there was any kind of regularity there. And there, if you follow this blue line there, that is a power law, which is indicative that there might be some level of order in there. But I mean, you got reflections coming off these things. You got, blurry photo. There's 15 ways from Sunday. You can't rely on that alone. And there's this other thing called Voronoi tessellations, which are used for identifying quasicrystals. I have such a limited amount of experience with these, but the gist is that you're basically showing like the overall distances between all these dots relative to their other neighboring dots. And if it was quasicrystal, you should see some level of regularity in there. On the top here, I got for the dots on that first picture sample. And down here, here's just a random one GPT came up with to show the difference between the two. And I think they look kind of similar, but there are a couple of spots that draw my attention. That's like right around here where you're starting to see some regularity. And then right here, you're starting to, again, see some of this regularity that if you come over here and you look at these lines here, it seems like it. I don't know. Once again, not going to rely on the Voronoi. So then we go on the radiuses, right? If you start drawing circles on this, is there regularity to the distances away from a center of position at which a lot of dots start falling on those circles of certain radii? And sure enough, if you look at these peaks here, we start seeing some level of regularity. I'm not going to rely on that. The most important thing that you need to do is you need to do fast Fourier transform. So here's a picture I took from a YouTube video where a guy's showing how to do this. Over here on the left, you can see he's got a picture of a quasicrystal going on. And then he's saying that normally with material science quasicrystals like this, you never get nice, pretty Fourier transform photos. They're always like rotated all over the place. So normally what you'll see is these rings of different radii showing up on your FFT. So here I downloaded some FFT, some image analysis software, and started doing some FFT. Down here, you can see this yellow square here is the area that I selected because we've got all that crummy noise on the edges and the corners of that image. But just from this red, you can kind of see those lines and dots a little easier, I think. Anyways, the X and Y axis bright lines you see here indicating, the frequency at which it's taking a lot of readings. That's in part because you're just getting pixelation, right? It's a picture of a picture. So ignore those vertical and horizontal lines there. The more important thing is how we have kind of some of these darker rings in here, and they're very faint, and I've contrast enhanced this photo over here to make it more obvious, but it's super faint. I think it's there, but it's super duper faint. We are not at smoking gun. We are at barely a warm steaming barrel. So that's for this QC1 image. And then for the QC2 image that has those two vertical lines and the triangle thing over there, once again, I did some of this contrast enhancing of the original FFT. And once again, very, very faint, but I think it's there. Some things that kind of look like shells, some potential for some periodicity, which once again, not a smoking gun, but enough to make me convinced that it's worth continuing to pursue. And then I was able to pull this FFT image out of it. And this is where I start getting really excited. So you can kind of see we got some of these weird darker pockets in here, right? And if you look at the white area here, you're starting to get like this weird tower shape. So what I've done is I've kind of outlined that, make it a little easier for you to see that, yeah, there is some kind of geometry going on with those dots. And while we do have those rings, we also have some of these really weird additional shapes coming out on the outside highest order of those. So if they are quasicrystals, it's a really high order quasicrystal. So now I'm just going to kind of riff for a bit, and I'm going to take you down to the bottom of the Marianas Trench of the Kool-Aid rabbit hole. So hold on. So quasicrystals, it just so happens that prime numbers are described with this thing called the Riemann zeta function. It turns out that the aperiodic nature of those prime number zeros on the Riemann zeta function act like a quasicrystal. So that's cool. Quasicrystals and prime numbers have a relationship. What? What else has a relationship with quasicrystals or prime numbers? Turns out that the shells of the hydrogen atom seem to follow some similarity to prime numbers. Wait a minute. So the most fundamental atoms we got have some prime numbers built into them, and prime numbers just so happen to be related to quasicrystals? Okay, that's weird. What else is related to it? Oh, DNA happens to have prime numbers in it. You can use prime numbers to describe DNA. Well, that's getting really weird. So atoms and DNA and prime numbers all seem to have relationships to quasicrystals. What else has a relationship to quasicrystals? Oh, the microtubules thing from Penrose? That happens to seem to have some quasicrystal element playing a role in there. So consciousness, DNA, atoms, prime numbers, all related to quasicrystals. Oh, I'm losing my mind here with just how many things are related to quasicrystals. I'm seeing them stinking everywhere now. Anyways, so going back to actual engineering stuff. So I started tinkering around with making my own quasicrystals here. My goal is that if I can print out some of these and I can try to wire them up in such a way, I might be able to see if I can't play around with some of Drew's stuff. And if nothing else, I just want to see if the electric fields that you get off of a quasicrystal are like super non-uniform and like create all these overlapping hotspots, and maybe that's usable. I don't know. So I've done another one here. I think this one looks a lot better. It's got some really high density to it. Quasicrystals happen to have some of the highest packing density that you can get, which is also really interesting and useful a million ways from Sunday. If you want to read more, I got like a 27-page Google Doc of just all these different quasi-crystal papers I've been collecting. If you want the link to this presentation, I made a tiny URL for it there. You can see UFO-QCS-presentation.
I just forwarded you earlier today. I forwarded you an email from Clee Irwin, who was talking about quasicrystals being a three-dimensional representation of higher dimensional matrices. So,
yes, so him and David Chester worked with Clee for a while there, and their work really inspired me in a lot of different ways. They show that at this higher level of reality, this mathematical abstract level of reality, geometries of quasicrystals seem to coalesce to take shape to explain all of the fundamental particle interactions that we see. Garrett Lisi's E8 model is another example of a quasi-crystal interaction in that way. So yeah, if you can somehow tie, this is where like just marinate yourself in the Kool-Aid. If you can somehow tie the most fundamental abstract, like metaphysical level of reality of math into particles, into atoms, into DNA, into microtubules for consciousness, like that's amazing. And the fact that it all relies on the golden ratio, I mean, come on, eat your woo heart out here, man.
yeah, well, there we go. But Jared, it's absolutely amazing. And you are working on a meta study, right? And Steve Colburn has provided you with tons of data, and we're going to be looking at samples. So we've got a ton of stuff. It's just putting pieces together, right? So